Welcome to my YouTube channel on designing and building machine learning systems. My name is Manoranjan Pradhan. In this video, we will discuss about the prediction patterns of machine learning systems and how it influences the design and deployment considerations. So there are machine learning models whose predictions are integrated into real-time business workflows. For example, delivery time estimation for a food delivery service, or estimating the expected arrival time for cab booking, or finding a fraudulent transaction. These predictions are very critical for the completion of an end to end business workflow. Based on the prediction of a fraud detection model, either the transaction will be approved or rejected, or based on the expected arrival time of a cab, either the user will book the cab or not book the cab. So these inference systems has to predict as soon as the request comes, and these are called online predictions. One of the key expectations from the model is to predict within a short span of time, especially few milliseconds, and this is called prediction latency. If the time at which the model receives a request to make prediction is t0, and the time at which the model sends back the prediction is t1, so t1 minus t0 is called the prediction latency. If you have built a complex model like an ensemble of hundreds of models, or a very large deep learning model which gives the best accuracy but cannot predict within the required latency, then it cannot be deployed and hence is not useful. And this latency can be inclusive of the time required to pre-process the data and feature to make predictions. Hence, it is advisable to do a performance benchmarking test of the models to ascertain whether the model can fulfill the expected latency requirement besides the accuracy. Also, the availability of these inference systems are very critical because any failure can lead to unavailability of the real-time business workflows. The other model prediction strategy is called offline or batch prediction, in which the model itself is not integrated with the real-time workflow. The predictions are made offline and in a batch mode, like end of the day or end of the month, and then stored in a file or database and made available for consumption later. Take an example of product recommendation system, which takes input of all customer purchases, then generates the recommendations, and these recommendations are stored in a database, and then the application reads these recommendations from the database and shows to the customers when they visit the site next. Another example would be customer churn analysis, in which the inference system at the end of every month will use the customer's behavioral data for the last few months and make a prediction whether the customer would churn or not churn. And then these predictions are made available to the business later to make interventions like running a promotion to retain those customers. In these systems, how quickly a prediction is made is not important. Rather, how many predictions can be made within a specified batch duration is important, which is known as the throughput of a system. So if we take the example of product recommendation system, the task of generating recommendations will actually involve a series of steps, like the customer's past purchase data or behavioral data has to be stored into a data warehouse or data lakes, and the inference or prediction system will take that data and generate necessary features to make the predictions. And then those predictions or recommendations will be stored into the database like RDBMS or NoSQL systems, which then will be made available to the applications in the real time. And all these steps will actually has to be completed within few hours in batch mode. And out of that, the actual generating predictions or recommendations will have to be done within an hour or two. As you can see, in online and offline predictions, besides accuracy, the other system requirements like latency and throughput of a system can actually influence the model development process, the choice of the models. One of the classic example of how engineering effort required for model deployment can actually influence the model selection process is Netflix movie recommendations. Netflix opened a challenge and offered a prize money of $1 million to predict the user rating for those movies and shows which the users have not watched yet, which will help Netflix make appropriate recommendations to the users in anticipation that they will actually watch those movies and shows and help generate more revenue for Netflix. There are many teams who participated in the challenge, and one of the team actually developed a model which had an error of 0.8567, which is a root mean squared error. And the model was far better than the one that Netflix already had developed and deployed in house. And of course, the expectation would be that Netflix would have actually gone ahead and deployed this model for which they have paid $1 million. But one of the news reads Netflix never used its $1 million algorithm due to engineering costs. And if you read one of the blogs that Netflix has written, I have given the link in the description page of the YouTube video. The team which won the first prize actually had an improvement of 8.43%. They spent about 2000 hours of work in order to come up with a final combination of 107 algorithms, which gave them this prize. If you read the blog further, they mentioned that we have evaluated some of the new methods offline, but the additional accuracy gains that we measured did not seem to justify the engineering effort needed to bring them into a production environment. So, accuracy alone does not drive the model development process. As you have already seen, a very low latency is required for online predictions and high throughput is required for offline predictions. There are also other scenarios when you have to deploy a model on an edge device like a mobile phone or a smart camera or smart watches or IoT devices. For example, a model deployed on a smart camera can actually detect a threat or an intrusion, or a model deployed on an IoT device can detect an impending failure or a defect on an assembly line and then shuts down the machine and prevents an accident or damage that may occur. There are also scenarios in which deploying a model on the edge device is a good idea. For example, when the user data cannot be transmitted to the server for privacy concerns, or the internet bandwidth is limited and the device cannot reach the server to make a prediction. One of the key challenges of deploying models on the edge devices is the limitation of computational resources. The size and the complexity of the model is highly constrained when it comes to deploying a model on the edge device. One way to deal with the limited amount of resources on the edge device is to adopt a two-phase prediction where A smaller model can be deployed on the edge device with a limited scope of predictions, and the request can be sent to the server for an extended scope of prediction. One of the best example is the home assistant device like Alexa or Google Home. So when you say okay Google or hi Alexa, the assistant has to immediately recognize the speech and wake up. Or if you ask a simple question like what time of the day it is, it can recognize the speech and respond back immediately. But if you ask a complex question like what is the weather is going to be like in Bangalore for the next 2 weeks, or can you translate this message to another language, then it has to send that request or speech to the server. The server detects the speech and responds back. Another example would be you can deploy a small model on the IoT device on assembly line, which can listen to the sound or vibration patterns of the machines and detect an impending failure and shuts down the machine to prevent any damage or accident. Or the same sound or vibration pattern can be sent to a server later to detect the actual category of the defect and initiate the necessary maintenance to fix the defect. So this week we discussed about the prediction patterns of machine learning systems. Some of the key points are online predictions, offline or batch predictions, predictions on edge devices, and two-phase predictions. So see you in the next video with a new topic. Thank you.